All right, we've been talking about center of mass for a while. What if I have two objects, one of mass m and one of mass little m? We're going to identify the center of mass of each object. In this case, they're both regular shaped objects, so that will be at their centers. Okay, so then I can identify origin. Let's say my origin's over here. And then x1 will be the distance to that center of mass, and x2 will be the distance to that center of mass. So if I want to calculate the center of mass of this object, Cx, and I'm calling that number 1, would equal mx1 plus mx2, okay, divided by m plus m on the bottom. I'm going to try to make these look more like 1s here. There you go. So I'm going to take the mass times the coordinate plus mass times the coordinate divided by the two masses added up together. Now what if my mass moves? This one's the one that moves and it's located here. Okay, I'm going to call that one like x prime. It's got a new distance now. Okay, so then my center of gravity in the x direction, or center of mass, we'll call this one number 2, will then equal m times x with a prime on it. Okay, plus mx2. And of course, we're just going to divide them by the same masses, m plus m. Okay. Now, what if I wanted to get the velocity of the center of mass? Well, then I'll just take cx2 minus cx1, and I'll just divide by time. So essentially, where did the center of mass move to? I'm taking the difference between those two spots and just dividing by time, just like I would with any kind of velocity that I would want to calculate. Velocity is distance over time. Now this one's special for my mechanics C class. What if I have an irregularly shaped object and I want to find its center of mass? Well, what we need to do then is do an integral. So the center of mass of this object, of course, is going to equal the integral of dm times x over the integral of dm. Okay, let's say we have something that's non-linear this time, and this definitely looks non-linear. Okay, so what if I define a lambda as equal to some constant b times x? Okay, so then I need to look at lambda again. Lambda, of course, is going to equal to m over L, the length of this. Okay, and we can even, to keep our variables somewhat consistent, we can go lambda over x, I suppose. Okay, so then dm is going to equal lambda dx. Okay, so then what am I going to do? I'm going to plug that into here. So my center of mass in the x direction is then going to equal, now I'm going to put in for lambda bx because lambda depends on x. So then I have bx. Okay, and I'm going to then multiply that by x. Okay, and then I'll have a dx in there. Okay, and I'm going to divide this. Okay, and that's going to be an integral. And I guess from 0 to L, if this is our length L, I suppose, from there to there is length L. And I'll divide this by the integral, okay, now this is just going to be dm then, right? Okay, so dm is going to then be bx and then times by dx. And this, of course, is going to be 0 to L also. Okay? So we're going to end up with a situation here where we have a 1/2, actually a 1/3 b x cubed on the top, okay, divided by 1/2 bx squared on the bottom once we take the integral of this. Now the definite integral here is going to be from 0 to L, and the definite integral here is going to be from 0 to L. Okay, so then we're going to have 1/3, okay, it looks to me like b times L cubed divided by 1/2 BL squared. And when all is said and done, it looks to me like that half will come up there. It looks to me like we're going to be 2/3 L is going to be the center of mass for this object. Okay, so that would be a quick integral. Now again, that's for mechanics only.